Welcome all to the BKR chemistry classes. Today we are going to see Favorskii rearrangement. It is one of my favorite reaction. Basically, what is Favorskii rearrangement? It is rearrangement of alpha haloketones. Alpha haloketones to esters. For example, if I take CH3 C double bond O CH2 Br to CH3 CH2 C double bond O O ET, that is in presence of sodium ethoxide, which will act as a base. We also need a proton source. For that we have taken ethanol. So basically Favorskii rearrangement is conversion of alpha haloketones to esters. It looks very simple, isn't it? But let us look into the molecules. Here we had CH3, COCH2, and now the molecule is completely rearranged. We have CH3, CH2, COET. This CH2 has come from this position to this, here to here, something like that. It's complete rearrangement of the carbon skeleton. Now let us see how it happens. So basically for this particular rearrangement, we require a base and we have taken the ethoxide, sodium ethoxide. We can also go for sodium methoxide. We can also take sodium hydroxide. If I take sodium methoxide, I'll get CH3, CH2, C double bond O, OME. That is methyl ester. If I take sodium hydroxide, I'll get CH3, CH2, COOH. It is carboxylic acid. So depending upon the reagent, I'll be having the variety of products. Now, let us see the mechanism, like how exactly this rearrangement takes place. So the first step of the mechanism is formation of carb anion. Formation of carb anion. So let me take the same starting material in presence of base. So the base will abstract the proton and I'll be having the formation of carb anion. So this is the first step. So let me write in a form that is very easy for you to understand in the format of mechanism. So this is the carb anion formed. The second step, the second step of the mechanism is intramolecular, intramolecular nucleophilic attack. Intramolecular nucleophilic attack. So I have this carbanion, it will attack the carbon containing halogen, Br will be released out, and I'll be having the formation of cyclopropanone intermediate. Cyclopropanone intermediate. So this is cyclopropanone intermediate. So this is the second step. So second step involves the formation of cyclopropanone intermediate. So since I've taken the molecule such a way that I'm getting a symmetrical cyclopropanone. Symmetrical cyclopropanone. This point is very important because I let you know this symmetrical cyclopropanone, if I make it as unsymmetrical, I'll be having totally changeover of the product. So we have seen the formation of cyclopropanone intermediate. This on reaction with the base ethoxide ion gives the tetrahedral intermediate. Tetrahedral intermediate. The cyclopropane ring has CH2 on both the sides. The ethoxide ion attacks the carbon because carbon is electrophilic. Since oxygen is more electron withdrawing, it gets the partial negative charge and carbon gets the partial positive charge. So this tetrahedral intermediate, when the O minus reverts back, I can have cleavage on both the sides. I can have cleavage either like this or I can have cleavage like this. So this bond can cleave or this bond can cleave. So when this O minus reverts, I can have either this cleavage. Suppose I take this A cleavage, or I can have this cleavage. I can take this as B cleavage. Both the cleavage are same. That is A and B cleavage are same because on both the sides you have only CH2. So the product which I get is COOET, ester, ethyl ester. And I have, suppose I take this cleavage of this particular bond, the carbon of the ester will be attached to the CH2 and I'll be having the carbanion. This in the presence of proton source, I'll be having formation of the ester. So what I've got here, I've got the ethyl propionate. So what we have seen here, we have seen the conversion of alpha haloketone in presence of sodium ethoxide and ethanol to give you the ester with complete change in the carbon skeleton. That is why it is known as rearrangement. In the next example, we will see the formation of unsymmetrical propanone and thereby the variation which occurs because of the unsymmetry of the propanone intermediate. So let me take an example which gives an unsymmetrical cyclopropanone. So in presence of base, same as the previous mechanism, I'll be having abstraction of proton, giving rise to a carb anion. Carb anion. Then the second step is intramolecular nucleophilic attack, giving rise to the cyclopropanone intermediate. So on the one side I have CH2, but the other side I have CH and phenyl. So I have a different moiety here. So I have a CH and phenyl. Now you can just recall. In the previous case we had a symmetrical ketone, but here we have got an unsymmetrical cyclopropanone intermediate. Now this will be attacked by sodium ethoxide. So I'll be having attack of the OET minus and I'll be having formation of the tetrahedral intermediate which has CH2 on one side of the cyclopropane, the other side I have a hydrogen and a phenyl ring Now when this O minus reverts back, I can have cleavage on this side which I take as A cleavage, or I can have cleavage on this side which I'll take as B. So the cyclopropene can cleave on A and B, and the cleavage of A and B are different. So suppose I have the shift of electrons like this, or I can have shift of electrons to this particular carbon. So I can have two different progress which can be visualized. Suppose I have A cleavage. I'll be having so this is a carbon which contains the ester COET. So since A bond has cleaved and the electrons are shifted to the CH2, this carbon will be attached to the phenyl containing carbon. Phenyl containing carbon. And the phenyl carbon is attached to the CH2 carbon. And the CH2 carries a negative charge. So this is carbanion 1. Suppose it goes via the B cleavage. B cleavage. Okay, so in this case, I'll be having COET. Since the carbon bond between the phenyl ring carbon and the double bond O carbon has cleaved, the carbon will be attached to the CH2 carbon. Is it not? So I'll be having CH2 followed by CH and phenyl ring with a negative charge. Now here I have two different intermediates, carbanion 1 and carbanion 2. Now the question rises, which is more stable? So in the symmetrical ketone, we didn't have such problem. You cleave on the either side, you have same carbanion. So there's no question of stability of carbanion comparison. But here we can compare the stability of the carbanion 1 and the carbanion 2. We can compare them. So as you can see, the carbanion 2 is more stable because the carbanion 2 is involved in resonance with the benzene ring. It is resonance stabilized. So you have a CH minus attached to a benzene ring. You have the resonance, complete resonance. So highly stable, highly stable. So compared to 1, 2 is more stable than 1. So 2 is the preferred intermediate. For B is a preferred cleavage. So B is a preferred cleavage. So now this second carbanion will take up a proton from the proton source to give you the required product. So this is the product. So this will be not formed. This cleavage will not take place. This is all based on the stability of the carbanium. Okay. Hope you have understood the mechanism in clarity. If you have any doubts in the mechanism, you can post that in the comment section. If you want me to talk on any other topic of your choice, you can also post that in the comment section. The next video I'll talk about quasi-Favorskii rearrangement. Quasi, very similar to Favorskii, but there will be slight variation. So that is also important. Hope this video was very useful to you.